Imagine looking up at the familiar night sky, a canvas of silent, twinkling lights. Now, imagine that some of those stars are not just shining, but are caught in a slow, strange, and perpetual rain. This is not a rain of water as we know it on Earth, but a cosmic downpour of something far more profound. It is a rain of broken rocks, shattered asteroids, even vaporized metals from planets that no longer exist. This is not science fiction. It is a reality that astronomers are now observing across the vast, dark oceans of space. The signs are subtle, whispered in the light from distant suns, but they tell a dramatic story. It is a tale of cosmic death, planetary destruction, and the constant, relentless recycling of matter. Here is a fact that might shift your perspective on the heavens. Some dead stars, the quiet embers of once mighty suns, are actively drinking the remains of their own planetary systems. The pieces of these long-lost worlds spiral inward, pulled by an unyielding gravitational grip, and fall onto the star's surface like a steady, silent drizzle. The star then consumes these planetary fragments. In the process, the star's own light changes, revealing the very elements it has just eaten. This is absolutely true. We can read this story written in the light itself. The light becomes a code, a cosmic message in a bottle, telling us about the last meal of a dying star. To grasp this incredible phenomenon, we must first meet the main character in this story, the white dwarf. A white dwarf is the small, incredibly dense core left behind after a star like our Sun has exhausted its fuel and shed its outer layers. It is the final smoldering stage of a star's life. Though it is small, often no bigger than our Earth, it is immensely heavy and possesses a powerful gravitational field. This gravity acts like a cosmic vacuum cleaner, pulling in any nearby debris that survived the star's death throes. This debris, asteroids, comets, pieces of planets, falls inexorably toward the white dwarf, creating a kind of celestial rain. We sometimes call this process white dwarf pollution. A pristine white dwarf should have a very clean atmosphere, composed mostly of the lightest elements like hydrogen, helium. Heavier elements, which astronomers call metals, should sink quickly beneath the surface due to the star's intense gravity. Iron, silicon, calcium. So, when our telescopes detect these heavy elements lingering on the surface, it is a smoking gun. It tells us they must be arriving constantly, replenished by an external source. That source is a rain of rocky material, the ghosts of a solar system that once was, falling onto the stellar remnant. The light becomes a code, a cosmic message in a bottle, telling us about the last meal of a dying star. Let us dive deeper into this first kind of star rain, the one that falls on white dwarfs. The process is both gentle and cataclysmic, playing out over millions of years. When a star like our Sun reaches the end of its life, it expands into a red giant, engulfing its inner planets. For eons, they orbit the newly formed white dwarf in a reconfigured, chaotic system. Gravitational nudges from surviving giant planets send smaller rocky bodies careening off course, on a collision course with the dead central star. A rocky body, maybe as big as a large asteroid or even a small moon, gets too close and encounters immense tidal forces. The white dwarf's gravity pulls harder on the near side than the far side. That differential pull stretches and elongates the object, then tears it apart into a stream of dust, gas, and rubble. The debris doesn't fall straight down. It settles into a flat, spinning disk around the white dwarf, much like Saturn's rings, but made of pulverized planetary remains. This debris disk is the reservoir for the star rain. From that swirling disk, the material slowly loses energy and spirals inward, raining onto the white dwarf's atmosphere. It's a very slow, continuous accretion, not a sudden splash. Less like a thunderstorm, more like a fine, persistent mist of rock and metal settling. Iron from a planet's core, silicon, oxygen from its crust, magnesium from its mantle enter the star's hot atmosphere and vaporize, becoming part of it. They leave a temporary, telltale signature in the star's light, a chemical fingerprint of the world that was consumed. This gives us an extraordinary tool. By analyzing this star rain, we can perform a stellar autopsy on an alien planet. We can determine if it was rocky like Earth, rich in certain metals, or if it contained building blocks of life, like water. There is another, far more violent and dramatic form of star rain that occurs in the universe, one that unfolds not around a dead star, but in the clutches of the most extreme objects we know: supermassive black holes. At the center of most large galaxies, including our own Milky Way, lurks a black hole millions, even billions, of times the mass of our Sun. These cosmic monsters lie mostly dormant, but occasionally, an unlucky star wanders too close. When this happens, the result is a spectacular and terrifying event, a tidal disruption event, a TDE. It is a star rain of unimaginable proportions. As the star approaches, the gravitational gradient becomes overwhelming. Astronomers call this spaghettification. Some material is flung away, about half falls back to form a superheated accretion disk. It glows across the electromagnetic spectrum, producing a brilliant flare that can outshine the entire host galaxy for months, even years. Telescopes on Earth and in orbit detect these sudden, bright flashes. Watching the flare brighten and fade lets us measure the black hole's mass, even its spin, and learn the shredded star's composition. The concept of star rain is not limited to stars or black holes. On ultra-hot Jupiters like WASP-76b, iron vapor on the blistering day side is swept to the night side, cools, condenses, and may literally fall as rain. Droplets of liquid iron. So, how exactly do scientists, standing on Earth millions of light years away, know that a star is eating its own planets? The answer lies in a powerful technique called spectroscopy. We do not see the rain directly. Instead, we see its effect on the star's light. A spectrograph splits starlight into a spectrum crossed by thin, dark lines, absorption lines. Each element creates a unique barcode of lines: iron, calcium, magnesium. A white dwarf's gravity should leave a clean H or He atmosphere. Metals mean fresh infall from a debris disk. Visible light spectra reveal the metals. Infrared telescopes see the warm, dusty disk feeding the rain. One remarkable case involved a white dwarf named GD61. Its atmosphere held far more oxygen than rocky oxides could explain. The best explanation? Water, H2O, in the debris. The accreted body was likely about 26% water by mass, similar to the water fraction of large asteroids like Ceres. This is a direct sign that water-rich bodies exist in other planetary systems. Such bodies may have delivered oceans to many rocky worlds, not just ours. The rain on a dead star tells us about the potential for life around living ones. If discoveries like these move you, tap subscribe, like, and share. Your support helps us keep decoding the universe together. Drop your questions below. Your curiosity fuels the next breakthrough. When we step back and look at all these different forms of star rain, a unifying theme emerges. The universe is in a constant state of recycling. Nothing is ever truly lost. The atoms that made up a planet can become part of a star. Material torn from a star by a black hole can be flung back out, later to seed new stars and planets. The same physics, gravity, heat, motion, drives rain on Earth and deluges among the stars. We still find white dwarfs with strange pollution patterns we cannot explain, and tidal disruptions that defy our models. We theorize even more exotic rains on distant worlds. Mystery isn't failure, it's the engine that drives better telescopes and bolder ideas. The next time you look at the night sky, remember, you're seeing a vast, interconnected ecosystem. The atoms in your body were forged in stars. We are literally stardust. Which star rain grips your imagination more? The slow, ghostly drizzle onto white dwarfs, or the violent flares of a black hole feast? Tell us in the comments. If this journey moved you, please subscribe, like, and share. It truly helps our community grow. Your support lets us keep bringing you stories from the frontiers of science. Keep looking up. The universe has so many more stories to tell.